The giraffe is a mistake that lived. Every rule of mammal design says an animal built like this shouldn't work. The heart shouldn't hold. The brain shouldn't get blood. The neck shouldn't stand up under its own weight. And if it did, drinking water should kill it. And yet, right now, out on the savannas of Africa, there are around 117,000 of them walking around, eating leaves, and looking absolutely fine. We tend to file the giraffe under gentle cartoon animal, long neck, funny walk, cute face. That's the version we grew up with. The version paleontologists and physiologists know is different. The giraffe is one of the most engineered animals alive, a machine built to solve a set of problems that shouldn't have solutions. And the more you look at it, the less sense it makes. That's what this video is about. Not the postcard giraffe, the actual giraffe, the one that shouldn't exist. Let's start with the number that stops every biologist in their tracks. A giraffe's brain sits about 6 feet above its heart. In a full-grown male, the top of the skull is close to 18 feet off the ground. Taller than a 2-story house is wide. The heart is roughly at the middle of the chest. That gap, that vertical column of blood between the pump and the brain, is longer than any other land animal has ever had to deal with. Now think about what that means. Gravity pulls blood down. To get blood up 6 feet to the brain against gravity, the heart has to shove it there with real force. In a human, average blood pressure is about 120/80. In a giraffe, it's roughly 200 to 250 at the heart, enough pressure that if a doctor measured it on you, they'd be prepping you for a stroke on the spot. In the giraffe, that's just Tuesday. To generate that pressure, the giraffe needs a heart that isn't playing by normal rules. It weighs up to 25 pounds, about the weight of a Thanksgiving turkey, and it's built with left ventricle walls thick enough to punch blood straight up a 2-story hallway. It's not just larger, it's reinforced. Cardiologists studying giraffe hearts have noted that the wall of the left ventricle is disproportionately thickened, and this thickening scales with neck length. Longer neck, thicker wall, higher pressure. The whole animal is a solved equation. We haven't even gotten to the hard part yet. Because that same pressure, the pressure that keeps the brain alive when the head is up, becomes a lethal weapon the moment the head goes down. And the head has to go down. Every animal has to drink. Watch a giraffe drink water. It's an awkward, deliberate, almost embarrassing thing. The front legs splay out wide. The neck bends. The head drops all the way to the ground. Sometimes it takes 15 or 20 seconds of adjustment before the mouth even touches the water. There's a reason for the caution. If a giraffe just dropped its head like a horse, all that pressurized blood already being shoved uphill would suddenly have gravity on its side. It would fall into the brain like a wave hitting a wall. The result would be a stroke, or worse, a burst vessel. Instant death by drinking. So evolution built the giraffe a hydraulic override. At the base of the brain, the giraffe has a dense mesh of small blood vessels called the rete mirabile, pronounced R-E-E-T mirabile, which translates roughly to wonderful net. It's a pressure buffer. When the head drops and blood surges downward, the rete expands and absorbs the wave, spreading it across hundreds of tiny vessels instead of dumping it into one soft brain. At the same time, valves in the jugular veins snap shut, trapping over a quart of blood in the neck itself so it doesn't slosh into the skull. Some researchers have suggested there's even a shunt, a kind of pressure release valve between the carotid and vertebral arteries that reroutes blood away from the brain during a drink. The full mechanism is still being worked out, but whatever the exact system, it works. The giraffe drinks, the giraffe stands back up, the giraffe doesn't die, which is amazing. And it should be enough to make the whole design impossible. It isn't, because now we have to talk about the legs. If the giraffe's problem above the heart is not enough pressure, its problem below the heart is way too much. That same 200+ pressure when it reaches the feet would blow the vessels in the ankles apart. Blood would pool in the lower legs like water in a sock. The tissue would swell up and split. It should be a fatal design flaw. The solution is one of the strangest workarounds in animal biology. The skin on a giraffe's lower legs is not normal skin. It's tight, dense, and non-elastic, wrapped around the leg like a permanent compression sock. It's the same trick a hospital uses on patients recovering from surgery to prevent blood from pooling, except the giraffe was born wearing them. Underneath that skin, the vessel walls are thickened and reinforced to survive the pressure. Astronauts wear pressure suits to keep their blood from misbehaving in microgravity. The giraffe wears one from birth. There's a story that got around in NASA circles that engineers actually studied giraffe legs to help design G-suits for fighter pilots. Whether or not the story is exactly true, the principle is real. The giraffe solved a hydraulics problem before we did, and it solved it with skin. And honestly, this is the part that still gets me. All of this, the heart, the pressure, the wonderful net, the valves, the compression skin, all of it is just infrastructure. It's just the plumbing needed to keep the neck alive. The neck itself is a whole other problem. And now the fact that breaks people the first time they hear it. A giraffe has the same number of neck vertebrae as you do. 7. That's it. The exact same count as a human, a mouse, a cat, a bat, a whale, and almost every other mammal on Earth. Blue whales have 7, mice have 7, bats have 7. The mammalian body plan is weirdly stubborn about this one number, and the giraffe kept it. The difference is that each of those 7 bones in a giraffe can be up to 10 inches long. 10 inches, each one about the length of a dinner plate. Stacked together, they build a neck that can stretch 6 to 8 feet, longer than the height of most NFL linebackers, on a single animal on top of legs that already put its shoulders over 10 feet off the ground. If a giraffe worked like most mammals, that neck wouldn't hold itself up. The muscles would burn out in an afternoon. The head would sag. But giraffes evolved a piece of anatomy called the nuchal ligament, which runs from the back of the skull all the way down the spine like a giant rubber band. It doesn't just support the neck, it holds it up passively, the way a suspension bridge holds up a road with cables. Cables don't get tired. Neither does the ligament. The giraffe barely has to think about it. The neck just floats. And it gets weirder. In 2016, a study out of the University of Tokyo found that giraffes have effectively cheated the mammalian body plan. Their first thoracic vertebra, the first bone of the rib cage in every other mammal, has been rebuilt to move like a neck bone. It still has ribs attached to it technically, but the joints between the ribs and the vertebra have been modified to allow real movement, and the muscle that pulls the neck downward attaches partly onto this thoracic bone. Anatomically, they still have 7 cervical vertebrae. Functionally, they have 8. They found extra flexibility by promoting a rib bone. It's the kind of thing evolution isn't supposed to be able to do casually. And the giraffe did it. Stand in front of one and try to take this in. You're looking at an 18-foot animal whose neck alone weighs several hundred pounds, held up by a ligament, powered by a 25-pound heart, drained by valved veins, and wrapped in compression sock skin. Nothing about that is normal. There is no other land mammal on Earth built this way. Not now, not in the fossil record. The giraffe stands alone. We haven't even talked about the mouth yet, because the giraffe eats a plant that is, in most other contexts, off-limits. Acacia trees are covered in inch-long thorns designed to stop exactly this kind of browser. Any other animal that tried to strip leaves off an acacia would end up with a bloody muzzle. The giraffe doesn't. It has a tongue up to 18 inches long, prehensile like a monkey's tail, colored blue-black on top to protect it from constant sun exposure. The lips are leathery. The saliva is thick and antiseptic, designed to coat and soothe any thorn that does get through. The giraffe walks up to a tree that has spent millions of years evolving weapons against being eaten, and it eats it anyway. It's a machine built to solve trees. Which leaves the obvious question, what was so valuable about being that tall that evolution went through all of this to get there? And the honest answer is, we're not entirely sure. The story you probably heard in school is the classic one. Giraffes evolved long necks to reach high leaves in acacia trees, outcompeting every other herbivore for the food no one else could touch. It's a clean story. Charles Darwin liked it. Generations of textbooks ran with it. And it's probably part of the answer. Giraffes really do feed on tall trees no other browsers can reach. That advantage is real, especially during dry seasons when low vegetation is stripped bare and every other browser is fighting over the same thinning bushes. The fossil record adds shape to that story. The giraffe family, the Giraffidae, pronounced Giraffe, goes back about 17 million years to an animal called Canthumerix, pronounced Canthumerix, a modestly long-necked browser found in what is now Africa. A few million years later, a fossil giraffid called Samotherium, pronounced Samotherium, walked the plains of what is now Greece with a neck about halfway between an okapi and a modern giraffe. The okapi, by the way, is the giraffe's only living cousin. It looks like a small horse with zebra-striped legs, lives in the Congo rainforest, and has a normal-sized neck. Looking at an okapi and looking at a giraffe, and knowing they share an ancestor, is one of the strangest side-by-side comparisons in mammal biology. One took the low road, the other went up. But there's a competing theory, and it's uglier. In 1996, two zoologists proposed that the giraffe's neck didn't evolve for food. It evolved for combat, specifically for a behavior called necking. When two male giraffes fight for mating rights, they don't wrestle, they don't bite. They stand next to each other, plant their legs wide, and swing their necks like sledgehammers. They aim their skulls at each other's necks, ribs and legs, the heads capped with bony ossicones. Hit like clubs, you can hear the impact from across the savannah. Bones break, skulls crack, sometimes males die. Under this theory, longer necks won fights and winners passed on their genes. The giraffe kept getting taller not to eat, but to hit harder. Then that theory took a hit of its own. Later studies looked at growth patterns between male and female giraffes. If necking were the main driver, males should have dramatically longer, thicker necks than females. Sexual selection almost always produces those kinds of differences, but the difference turned out to be smaller than expected. Both sexes grow similar necks, so the necks for sex hypothesis softened. Now most researchers think the truth is a mix. The neck probably evolved for feeding, and once it was long, males started using it as a weapon. Both pressures likely kept pushing. Even the feeding story has a twist. In 2025, biologists at the University of Adelaide and Pretoria published a paper that reframed the whole design. The giraffe's long legs, they found, weren't a side effect of the long neck. They came first. And they solve a real energy problem because the legs raise the heart higher off the ground. The vertical distance from heart to brain is shorter than it would be if only the neck had stretched. That saves the heart a huge amount of work. According to their numbers, the left ventricle already burns about 16% of the giraffe's resting energy just to pump blood upward. Without the long legs raising the heart, that cost would climb to 21%. The giraffe wasn't stretched randomly. It was stretched in the exact proportion that makes an animal this tall about as energy efficient as one can be. Now step back. The giraffe you saw at the zoo, the one your kids waved at, is running the most extreme cardiovascular system on land. It's carrying a neck that shouldn't hold. It's fighting off strokes every time it takes a drink. It's compressing its own legs with its own skin. It's using a ligament like a suspension bridge cable. It's cheated the mammalian body plan by promoting a rib to do a neck's job. And it did all of this over roughly 20 million years of ancestors that started as much shorter, chunkier animals and just kept getting taller. One more thing, because if all this hasn't convinced you the giraffe is a strange piece of machinery, this will. An adult giraffe can kick in almost any direction. Forward, sideways, backward. Most large prey animals can only kick one way. A horse kicks backward. A cow kicks straight back or sideways. A giraffe has no blind spot when it comes to hooves. That kick, delivered by a hoof the size of a dinner plate at the end of a leg the length of a grown adult, can generate enough force to shatter a lion's skull. Lions know it. Experienced lion prides only go after giraffes when they've caught one exhausted, cornered, sick, or asleep. Full-grown, healthy adult giraffes are functionally off the menu. Some lion prides in East Africa specialize in hunting them, the way certain killer whale pods specialize in hunting seals, but even those specialists lose members regularly to a well-placed kick. Picture the moment. A lion breaks cover and closes the distance. The giraffe doesn't panic. It doesn't run first. It squares up on those impossible legs, watches the cat for half a second, and drops one front hoof through the air with the leverage of an 18-foot lever arm. A cat weighing 400 pounds simply cannot survive being hit in the head by a mass that heavy, moving that fast, at the end of a limb that long. The tallest, gentlest-looking herbivore on the savanna is also the one that can kill an apex predator with a single well-placed strike, and it will. And the lions know it. Sleep for a giraffe is another design problem. They sleep about 30 minutes to an hour a day, mostly in short standing naps. Lying down leaves them helpless because getting back up on those long, splayed legs takes precious seconds. Seconds a lion doesn't need, so they mostly don't. They doze on their feet, one ear open, hearts still hammering blood uphill through the night. If you ever feel tired thinking about a bad night of sleep, remember the giraffe is running on 45 minutes a day and still fighting off apex predators in between. Here is where I have to be honest with you, because the giraffe, this improbable animal that shouldn't work and does, is disappearing. There are roughly 117,000 giraffes left in the wild, fewer than the number of people who live in a mid-sized American town, fewer than the seating capacity of the biggest college football stadium in the country. For an animal that ranges across an entire continent, that is not a lot. Habitat loss, poaching, and civil unrest across parts of Africa have driven several giraffe populations into what conservationists call silent extinction. Silent because most of us didn't notice it happening. We still think of giraffes as common. They aren't. Some subspecies now number in the hundreds, a few thousand in the whole world, spread across parks and reserves in a handful of countries, with poachers on one side and shrinking habitat on the other. The animal that solved the strangest engineering problem in the mammal kingdom, that generates blood pressure high enough to kill a person, that carries a neck built like a bridge and legs sheathed in compression skin, that survived 20 million years of predators and climate shifts, is being erased in a single human generation. Consider what we're losing. Not just a tall animal, a working solution to a set of problems most bodies aren't allowed to have. Every giraffe on Earth is a walking demonstration that biology can find answers to questions that shouldn't have answers. Take that away, and what disappears isn't only a species, it's a proof of concept. Evidence that shapes we assumed were impossible are quietly possible, just barely. The giraffe is a mistake that lived. For roughly 20 million years, evolution ran the impossible math and got a real animal out the other side. That animal is still standing on the savanna right now, hammering blood 6 feet uphill, kicking lions into next week and looking at us with those enormous dark eyes over the tops of trees no other mammal can touch. We should probably try to keep it around, if for no other reason than the fact that once it's gone, we'll never build anything like it again. Not with all the engineers on the planet. Thanks for watching, and I'll see you in the next one.